Good morning. Waiting for a couple more viewers before I get started. I've got this former student from my very first year of teaching who needs help with her homework. I think it's funny that I'm helping this, and so get this student majored in geology and actually has been a community college professor now, and I'm helping her with her homework because she's in a PhD program now. I still got it. All right, I'm going to go ahead and get started. Okay. I cannot stop yawning. Okay, let's get started. So the topic of today's lesson is something called rotational kinetic energy. All right. So rotational kinetic energy is in contrast to what's called translational kinetic energy. So translational kinetic energy is the kinetic energy that you know about. That's the 1/2 mv squared. Okay. But really, they're if something has kinetic energy, it can have kinetic energy if it's going from point A to point B. That's translational kinetic energy. Rotational kinetic energy is the energy of spinning in place. Okay? The faster you spin, the more rotational kinetic energy you have. So if we think about like a wheel, a spinning tire or something, that has rotational kinetic energy. Okay? if we think about a saw has rotational kinetic energy. It has an energy of spinning. A wind turbine has rotational kinetic energy. Okay? So rotational kinetic energy has to do with how fast you're spinning. Okay? So the kinetic energy of rotation is analogous to the translational kinetic energy. So you might recall that we talked about this analogy between linear motion and rotational motion. So the rotational analog of mass was inertia, and the rotational analog of linear speed was angular speed, omega. So this is the kinetic energy of rotation. And what it says is the faster you spin, the more rotational kinetic energy you have. Okay? We can transform from one type of kinetic energy to the other. Okay? If you think about how does a wind turbine work, you're taking the translational kinetic energy of wind. The wind is blowing from point A to point B. That's translational kinetic energy. And you're turning it into the rotational kinetic energy of the wind turbine. And then the rotational kinetic energy of the wind turbine turns into electrical energy, which then powers your house. Okay? So you can have one form turns into another form. All right? It's possible to have both forms of kinetic energy simultaneously. How could that happen? Well, what if I throw my calculator, and when I throw it, it's spinning while it goes from point A to point B. So it's going like this. Okay? You have both translational and rotational kinetic energy. And so in that case, your total kinetic energy is going to be the sum of your translational kinetic energy and your rotational kinetic energy. Okay? So that is your total kinetic energy. Now, most of the time translation and rotation are completely unrelated. Okay? If we think about an asteroid in outer space, asteroids are rotating and they're translating. Okay? Planets are rotating about their axis, they're spinning, and they're translating through outer space around the sun. Those two things are unrelated. But there is a case where they are related. And that is when something is rolling. So rolling, when you are rolling, translation and rotation are related to one another. Okay? And I should say that is rolling without slipping. Can you think of a situation? Well, let me just talk about this first. So here is the relationship. Okay? If you are rolling without slipping, and this is basically how an odometer works on your car. Okay? Your odometer on your car doesn't work with GPS, all right? It doesn't, they had odometers before GPS existed. The way that your odometer works on your car is it's counting how many times does the wheel spin, okay? And assuming that the wheel is rolling without slipping, then that correlates to a certain amount of distance traveled. Okay? And so to demonstrate this, I have this toilet paper roll of science. Okay? This is the toilet paper roll of science. This is very precious. I'm using a precious commodity right now. So let me make this full screen. So you can see I've made a mark on this toilet paper. Try and make it more. Okay, so there's a mark. And I'm going to have this toilet paper do one full rotation. Okay, so got the toilet paper. See how the toilet paper is straight up and down. Let me scoot this back so we can see the whole thing. All right. So the toilet paper is straight up and down. And we're going to do one full roll of the toilet paper. Okay, so we're going to wait until we're going to roll it until the line is back to the vertical. Okay. Oop. Did I go too far? Okay. So there, the line is back to the vertical. And so at that point, I'm going to break it off. All right. So this piece of toilet paper right here represents how far forward the toilet paper roll moved when I rotated it once. Did one full rotation, and because I let it unfurl, this is how far it moved. Okay, this is how far the toilet paper roll moved forward. So let's go ahead and figure it out. All right. If we look at it, I'm going to wrap this around, and we can see that, boom, it fits perfectly, or almost perfectly, with one full circumference. So if something is rolling, if it does one complete rotation, it moves forward by one circumference. And I know that this is one circumference because I can wrap it around exactly the toilet paper. Okay? Just came up with this demonstration last period, and I don't know why it took me 10 years to figure out that demonstration, because that's a perfect demonstration for that concept. Whoops, what did I do? Okay, so if you are rolling without slipping, if a wheel does one full spin, then it moves forward by one circumference. Okay, and we just proved that. We let it roll forward, we tore off the piece of toilet paper, and the length of that piece of toilet paper represented how far it moved forward. And then we compared that to the circumference. It wrapped around perfectly. Okay, so that means that the delta x for one rotation is going to be 2 pi r for one rotation. Okay. So now I can take this and I can divide it by time elapsed for one full rotation. All right. And so displacement over time, that's just speed. And then 2 pi over delta t, because we let it do one full rotation, that means that delta theta was equal to 2 pi. Okay, so this is delta theta over delta t, so that's omega, the angular speed. All right, so when something is rolling without slipping, its linear speed is related to its angular speed. Okay, its linear speed is related to its angular speed. And that's fairly obvious. So what this equation is saying is the faster the wheel is spinning, the faster the car is moving forward. Okay, if you look at the wheels on cars when they're on a freeway, the wheels are spinning very rapidly. If you look at the wheels on a car in a parking lot that's driving through a parking lot, you can see that they're moving much more slowly. All right. You'll probably be able to see the individual rotations of the wheel, whereas it just looks like a blur when you're on a freeway, right? And it's important that this is rolling. So this equation is true only when rolling, without slipping. Okay. If you can be rolling while slipping. So for example, in a car, you could peel out, or you could skid or drift in a car. Okay, and in those cases, this relationship will not be true. Okay, if you think about peeling out, you have the rotation rate of the wheels is really large because the wheels are spinning, but the car is not translating hardly at all. Okay, so peeling out, you have the right side of this equation is greater than the left side. Okay, when you're peeling out. What if you are skidding to a stop? If you are skidding to a stop, then the wheels are no longer spinning. Okay, because you've clamped the brakes down on the wheels so that they're no longer rotating, but the car is still translating forward. So you have that the left side is greater than the right side when you are skidding. Okay, so the only time you have equality is when you are rolling without slipping. And so we can take this equation and we can rearrange it. Okay. We can write it as omega equals v over r. Okay. And I'm going to use that and I'm going to plug it in to the equation for rotational kinetic energy. Okay. So if I have my equation for rotational kinetic energy, it's 1/2 I omega squared. Okay. And now I'm going to plug in v over r for omega. So I have 1/2 I times the quantity v over r squared. And so I'm going to square both of those. So I have 1/2 I v squared over r squared. And now I'm going to do something weird, which is I'm going to multiply by m and I'm going to divide by m. So I can do that because m over m is 1. And if I take something and I multiply it by 1, it doesn't change it. Okay? And then I'm just going to use the fact that multiplication, I can rearrange the things. And so I can write this as 1/2 mv squared times the quantity I over mr squared. So this is another weird way of writing the rotational kinetic energy. Okay? And so there's a reason why I'm going to do that. It's because your total kinetic energy is going to be the translational kinetic energy, which is 1/2 mv squared, plus the rotational kinetic energy, which I'm going to write it in this weird new form, which is 1/2 mv squared times the quantity I over mr squared. Okay? So why did I do it that way? Because now I can see that both terms have 1/2 mv squared. So I can factor that out. And when I factor it out from the first term, it's going to leave behind 1, right? Because this is 1/2 mv squared times 1. And when I factor it out of the second term, it's going to leave I over mr squared. So this is the kinetic energy when you are rolling is equal to 1/2 mv squared times the quantity 1 plus I over mr squared. All right? And so, yeah, so this ends up being the most useful form for the rolling kinetic energy. So again, this 1 comes from the translational part of the kinetic energy. And this I over mr squared comes from the rotational part of the kinetic energy. All right? So let's do a conservation of energy problem just as an example to show how this works. Okay? A solid disk rolls without slipping down a hill that is 40 meters high. It starts at rest. What is the speed at the bottom? Okay. What is the speed at the bottom? So let me draw a picture of what this looks like. We've got a hill. The hill is 40 meters high. Oops. 40 meters. Okay. We've got a solid disk. And it's going to roll down the bottom of the hill. Okay. And we want to know how fast is it going once it gets to the bottom. And so this is a conservation of energy problem. The energy at the top of the hill has to be equal to the energy at the bottom of the hill. At the top of the hill, we have gravitational potential energy. At the bottom of the hill, the wheel no longer has gravitational potential energy, but it has rolling kinetic energy. Okay. So now I'm going to plug in the forms of these equations. So you might recall that gravitational potential energy is mgy, and rolling kinetic energy, you just wrote it down right here, is 1/2 mv squared times the quantity 1 plus I over mr squared. So I can cancel out these masses. All right. Meow. 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 Okay. Now it might look like the answer depends on mass, but it actually doesn't. So let me show you why it does, because I didn't give you the mass of the solid disk. All right. So you might be panicking right now. You say, well, these two masses canceled out, but there's mass right there. What do I do? Okay. And so here's the thing. the inertia of a solid disk is given by 1/2 mr squared. Okay, that result comes from calculus. This is not a calculus-based class, so I would just give you that result. You're expected to use this, but you don't have to know why this is true. Okay, so just take it for granted that that's 1/2 mr squared. Okay, now if we divide both sides of that by mr squared, we get I of the solid disk equal over mr squared equals 1/2. Okay, so see how the inertia depends on the mass in such a way that it cancels out with this mass, and so the answer just doesn't depend on mass anymore. Okay, and so what that means is that 1 plus I over mr squared is going to be equal to 1 plus 1/2, which is just 3/2. Okay, so I have g times y equals 1/2 v squared, and then for the 1 plus I over mr squared, I just replace it with 3/2. All right, multiplying these fractions, I get g times y equals 3/4 v squared. And then I can solve this equation quite easily. So we get that v, multiply the 3/4 over, we get 4/3 gy, and then I have to take the square root. So that gives square root of 4/3 times 10 times 40. And I will plug that into my calculator. And we get 23 meters per second is the translational speed at the bottom of the hill. If we wanted to know what's the rotation rate at the bottom of the hill, we could then plug that into this equation, which relates rotational speed and translational speed. Okay. The physics of something that is slipping is much more difficult. So we won't ever consider the physics of something that is rolling and slipping while it is doing so. Okay. So one last thing I wanted to talk about today, which is let's suppose we have something that is sliding without friction. Okay. So something is sliding without friction. So kind of like a skier maybe. Skier with really, really slippery, well-waxed skis, or a well-waxed snowboard, versus something that rolls down an identical hill. So versus rolling without slipping. Okay, and so the question is, which is faster? All right. Now, if you think about rolling, in order to roll, well, let me just describe this a little bit better. So you kind of want to think about it as a skier who is sliding down a mountain. Okay, and this skier is not doing turns to slow themselves down. They're just going sliding straight down. Really well waxed skis, so there's no friction. Versus like a tire that is rolling down the hill without slipping. Okay? Like a traction tire. And it turns out that this one is going to be faster. Why is that? It's faster to slide without friction than it is to roll. So the skier would beat the tire that's rolling down the hill. So why is that? Well, if you think about it, in order to roll, you need to have friction. Okay? Because what is going to make, if there was no friction, we had this toilet paper roll on a hill, it would just start to slide. It would just go, it would slide. Friction is the thing that makes something start to roll to begin with, right? It's the force of friction that makes it fall over and start to roll, okay? So you can't be rolling. So in this case, you must have friction. All right, and friction is an oppositional force, so it's going to slow down the wheel. All right. Another way you can think about it is if you look at the energy. Here we have gravitational potential energy, all right, becomes translational kinetic energy. There is no rotational kinetic energy because the skier is not rotating unless they fall and then they start tumbling. But assuming the skier doesn't fall over, they're just translating down the hill, okay? Whereas in this case, we have potential energy becomes kinetic energy of translation plus kinetic energy of rotation. So the potential energy here is all of it. So if you started with 100 joules of potential energy, all of those 100 joules are going to become translational kinetic energy. Whereas here, you start out with 100 joules of potential energy, and maybe 80 of those joules goes into translational and 20 goes into rotational. So that the energy is going to two different spots, and so you don't end up with as much translation at the end. All right. So for that reason, sliding without friction is going to be faster than rolling without slipping. All right. So that is my lesson for today, and I will see you in the Zoom room.